This is the science show with Dr. Dada. It's just so nice, you cannot do without. This is the science show with Dr. Dada. It's just so nice, you cannot do without.
Well, hello, and welcome to the Science Show with Dr. Dada here on Jambo Radio Scotland, broadcasting right from the heart of the city of Glasgow. It's really nice to be back, and today we're going to be talking about something that's very, very current, very, very hot, and it is about quantum science and technology. You may or may not know that this year, 2025, has been declared the International Year of Quantum Science and Technology. And what that means is that on this show, you're going to be hearing a lot about quantum science and technology over the coming weeks and months. Today, what we're going to do is we're going to sort of lay the groundwork for that. We're going to talk about some concepts, some jargons, some code words, if you like, that you will hear a lot when you read literature or listen to anything to do with quantum science and technology. And we're going to do that without the fluff, without the math, without complicated explanations. We're just going to take it easy. We're going to make it cool and make it nice. And that's what we're going to be talking about today. So our title is Quantum Tech is Taking Over. But do you even speak the language? So we're going to break down the ABCs of quantum. And hopefully by the end of today's show, you'll be able to follow along. You'll become a bit of an expert when it comes to quantum science and technology. So, my name is Dr. Adetunmise Dada. I am a lecturer in optics and quantum technology at the University of Glasgow, and I love music as well. And here I am the host of the Science Show with Dr. Dada on Jambo Radio Scotland, and it's great to be here. It's fantastic to be here with you. Some of the concepts that we're going to be looking at today are basically some of the key words that you hear often when you're thinking about quantum technology. As you probably know, quantum technology is something that is set to change the way we do things. It's set to change the way we compute or we process information, the way that we solve the hard problems, and the way that we communicate information, the way that we safeguard our information, even the way that we do healthcare. For example, when it comes to, sensing technologies that we need to really look into the body and do diagnostics, all these aspects of our everyday lives are affected by quantum science and technology. And some of the basic ideas, the foundational or underpinning principles in quantum science and technology are actually quite simple. Although, because they're jargons, when you hear them, you're like, oh, okay. You hear them a lot. You hear about qubits and entanglement and superposition and this and that. And you wonder, you have an idea what it means. But sometimes it's easy to get the wrong idea, especially, in the media. You hear a lot of different people, content creators, who maybe don't state things exactly as they are. And what we're going to try to do today is to kind of bridge that gap, kind of explain it in a simple way, but also we'll try our best to make it as accurate as possible. So the first one that we're going to talk about today is the concept of a qubit. So we all probably are familiar with the idea of a bit. So a bit is a unit of information. It's the most fundamental unit of information. Everything we do, from sending a text message to sending an email, recording a video, sending a video, whatever we do that involves digital sort of communications or entertainment, it involves the use of these units of information, which are bits, right? And a bit is basically a physical system that can be in one of two states. So two possible states, and the bit can take one of the values. And we like to call the values 0 and 1 because it's a binary system. So 0 and 1, you can think of it in terms of, for example, a light switch which can be on or off. So that's a very nice example of a bit. And it could be the value of a pixel on a screen, a black and white screen. Pixel could be on or off, and so on and so forth. Now, it turns out that every form of information, and that might be anything from a picture, a JPEG picture, to a video, to even AI, a large language model, all these kinds of information or forms of information can be encoded in terms of bits, in terms of zeros and ones. And in fact, they are. A lot of the digital technology that we have today use zeros and ones to encode the information that we process, that we use, and so on. Now, having said that, when we talk about computing, so that is processing information in one way or the other, we use processors, computers. Okay, so everything that we have, for example, our phones, any device that processes information, essentially is a computer. And so that brings us to quantum computing, the quantum science and technology. What's the relationship between the bit that we know and the quantum version of the bit, which is called the qubit or quantum bit? Now, the quantum bit can also be in two possible states at once, or rather one of two possible states. So just like the bit, it can be 0 or it can be 1. But the different thing about the quantum bit is that sometimes it's not sure which state it's in. And we call that sort of situation, in describing that, we say that it's in a superposition of the two states. So imagine that you're getting dressed in the morning and you can't decide between your favorite red shirt or your comfy blue sweater. And when you're in this state of indecision, you don't know which one it is going to be. That's kind of how it is when a quantum system is in a superposition state. Basically what we mean is it's neither in 1 or in 0. It's kind of in both at the same time. And when people explain that, when they say, it's, a qubit is in two states at the same time, that could be a little bit misleading. So we have to be very careful how we explain it. And I think perhaps the best way to explain it is using some illustrations. I kind of like the idea of, something being undecided, right? So someone doesn't know whether they're going to say yes or they're going to say no. They're somewhere in between. They're not saying yes and no at the same time. It's just they've not made up their mind yet, if you like. So maybe there's a probability that they're going to say yes, there's a probability they're going to say no, but they just haven't, collapsed to that reality or a specific answer yet. So it's very similar when you talk about qubits. So it's not a case that it's it's in both states at the same time. As such, it's kind of not sure which state it's in. Mathematically, when you describe it, it's it's a lot more precise than that. So the state it's in is actually a very precise state. It's just that it's it turns out that you can describe it as a superposition of two sort of distinct states that we know, we can identify. So it's a bit like that. Another illustration that I like to use is when you flip a coin, right? If you have a coin, it's either heads or tails. When you flip it and it's in the air, you don't know whether it's head or tails yet. So while it's in the air, it's a bit like, it's similar to what you have when a qubit is in a superposition of 0 and 1. It's in both states at the same time. And if you want to think about it in terms of the position of a person, or of the decision a person makes. So for example, if you come to a crossroads, you can either go left or you can go right, and you're not sure which one you're going to pick. So when you're in a superposition, if you were a quantum particle, what you would do is kind of you don't decide yet. You go through the two options and you haven't decided yet which one you went through. So I'm sure you realize it's really weird. It's kind of weird, isn't it? It's like you go through both, but eventually you actually go through one of them. It's just that even after you've passed through the two options, you still are in a position where you haven't decided which one you went through. So that's a bit mind-bending, but that is how it behaves, and many experiments demonstrate that it behaves this way. So I think that's enough when it comes to understanding how a qubit works. Hopefully that's cleared some doubts, and hopefully it's kind of giving you a little bit of more understanding of how it works and what it does on a fundamental level. And with that, we're going to take a music break, and this music break is going to be, this song is very, very interesting. It's entitled Bolanles by Zlatan and IVD, and we'll be right back. Yes, welcome back to the Science Show with Dr. Dada. That was Zlatan with Bolanle. Yeah, that was a banger in the I wanted to say in the olden days. It's from 2020, I think, and it's just amazing how very quickly time passes, isn't it? I can't believe that song is from 2020. So that's Bolanle, a very nice Afrobeat track. And we've been talking about quantum technology, quantum science and technology, and some of the underpinning concepts. We've talked about a qubit, the fact that a qubit can be in state 0 and 1, in a superposition of state 0 and 1, which we like to say, well, it's kind of undecided where it is. It's in a precise state that you can kind of, in a hand-wavy way, describe as an undecided state between 0 and 1. But mathematically, it's very precise. There are different forms this kind of undecided state can take. But anyway, we'll move on to the next concept, and that is entanglement. You would have heard entanglement a lot. Entanglement is so massive in quantum science and technology. It's like the fuel on which the quantum computer runs, the fuel on which quantum communication, often a lot of the time, quantum communication runs on entanglement, quantum sensing, a lot of the magical things you do with quantum runs on entanglement. Quantum teleportation runs on entanglement. So what is entanglement? I'm going to use a very simple illustration that kind of gives us the idea. Let's use the illustration of two friends, two dancers, for example. And, one could be here in Glasgow and the other one could be in another place on Earth, or maybe on another planet, in another solar system, another galaxy. But just imagine, compare that situation to two dancers who are together in the same room and they're doing the tango. Usually when dancers dance, they kind of do things in synchronization, So the moves kind of are correlated. They're either doing the same thing or doing things that are kind of sort of complementary in some way, right? Now, imagine if they were far apart. So one here in Glasgow, another one on Mars or whatever, and they're doing the dance. It's very, very difficult to accept that they would somehow be able to, do the same moves or dance in a synchronized way. Because to do that, usually you need to kind of have some contact or some form of communication with each other, either by seeing each other and then you can sort of correlate what you're doing, or by listening to the same music, or maybe by having agreed beforehand the dance that you're going to do. But without agreeing beforehand, without doing any such thing, imagine having a situation where you have two such dancers and they can dance and they do that in perfect synchronization, even though they're so far apart, even though they're worlds apart, they're in two different galaxies or solar systems or whatever. So this is kind of what entanglement does. although with our normal intuition, our everyday common sense, you would say that kind of thing would be impossible, right? I mean, how would you manage to do that? And it turns out that actually the universe allows this kind of behavior to happen, not between people, as to our knowledge, but between quantum systems, quantum particles. Another illustration that maybe helps a bit with that is if you think about two coins, right? You have two coins, so you have one coin and you have the other one, and you flip both coins. It would be really, really weird if each time you flipped the two coins, these two coins would give you the same result every time. So you flip, and you get heads in one, you get heads in the other one. You flip again, you get tails in one, you get tails in the other one. And no matter how many times, each time you flip these coins, you always get the same result. That would be really, really weird. And even more weird would be if when you got heads in one and you get heads in the other one, if you separate them over a long distance, you put one here on Earth, you put another one on a spaceship and off to Jupiter or wherever, and they still continue to do that, even if they're miles or worlds apart. Well, that is super weird, and that is what entanglement does. Today we won't go into the how it actually works, how you do quantum teleportation. We might talk about that in a future episode, but I just want us to take away this idea of how entanglement works. It's always, there's a super correlation between the two particles that are entangled, but also, apart from this super correlation, this correlation persists no matter how far apart they are, and it's kind of instantaneous. So when you check one coin, the other one, even though if it was undecided a moment ago, the moment you check one and you find it heads, the other one collapses to heads. Someone expressed it in a really nice way. I can't remember who it was. I wish I remembered. It was a very well-respected quantum scientist, and what he said was that entanglement refers to the linking of destinies. So it's like these two coins, the destinies are linked. You've got one, it's either going to be heads or tails, you don't know yet, and the other one's either going to be heads or tails, you don't know yet. But whatever this becomes, the other one becomes. So that sort of correlation. So linked destinies. I really like that way of putting it. So this is, the way entanglement works. It leads to a lot of wonderful things. And, it's just absolutely amazing what you can do with entanglement. It powers a lot of the possibilities in quantum science and technology. We're going to talk about them more after the next music break. So now we're going to listen to a song which is kind of very popular in Afrobeat, in the Afrobeats world. Is entitled Joy is Coming. It's by Fido, and we'll be right back. Yeah, that's a really nice banger, isn't it? Joy is Coming by Fido. And this is the Science Show with Dr. Dada on Jambo Radio Scotland, broadcasting live from the city of Glasgow. And we would like to take this opportunity to remind you about, various ways in which you can engage with this show. We're online. We're online at jamboradio.co.uk, and episodes are uploaded onto our YouTube channel, Jambo Radio Scotland YouTube channel. Also for the show, we have a dedicated YouTube channel, and on all platforms you can reach us on that dedicated channel, and the handle is T Science Show. And so, be it X or Facebook or Instagram, TikTok, we're there, and you can see clips from the show as well as the various ways to engage with the show there. And yes, we encourage you to do that. We're of course broadcasting live, so DAB in your car, in your garden, in the house, wherever you are, you can catch the show. We have a rebroadcast throughout the week as well. 2 p.m. on a Wednesday, 7 p.m. on a Wednesday being broadcast times that we use, and others as well. You can see those on our show page on jamboradio.co.uk. So we've been talking about the quantum world, some of the weird aspects of the quantum world. We're trying to keep it cool and keep it nice, keep it simple as much as possible. And now we've come to the subject of quantum cryptography. So cryptography is something that we all use. We send our information and it's encrypted. We all know, or we've heard about encryption. It's very important because, that's what keeps your information from getting into the wrong hands. For example, when you're sending information to your bank, when you're banking, you need your password. So your password is part of the encryption process, the thing that keeps the information from, getting into someone else's hands. If they happen to copy it, they can't do anything with it, because without the password or the key, they can't decrypt the information. Now, in the way that we do that, before quantum technologies, quantum science, the way that we do that, it turns out that we base the security of these encryption protocols on the fact that some mathematical, functions or mathematical calculations are difficult, are really, really hard. So if you make the mathematical problem large enough, it will take forever, pretty much. It will take hundreds or thousands of years for someone to actually solve that problem. And so if you use that as a basis for your security, that means you generate a password that's very long and very difficult to crack. That is very difficult for someone to actually find the password. And when you do that, you hope that somebody doesn't have a super powerful computer that will just crack or, figure out what the password is very easily. So it turns out that, of course, that's not unconditionally secure. It is secure based on an assumption that the eavesdropper or whoever wants to crack your password is limited in the resources that they have. Now, wouldn't it be nice to have a situation where you don't have to make that assumption? Because, if you have to make that assumption, that means your encryption system is not future-proof. That means it's, in future, if computers get more and more powerful, your passwords, the encryption that you did a while back is not going to be holding up anymore. So this is where quantum cryptography comes in, because what quantum cryptography does is that it allows us to generate these, a special way to generate passwords. And these passwords, they are such that it's impossible for you to crack them, and they're, provably secure. You can prove their security, and it's unconditional. It's secure, it's future proof. No matter what advances you make, no matter how powerful computers get in future, quantum cryptography, this method of encryption that uses quantum, effect, uses quantum systems, it still holds. And that is massive. That's big. That's amazing, right? So it's a bit like, with entanglement. We talked about entanglement. We talked about quantum superpositions. Some of the properties of quantum systems. Of course, we've talked about these first two, that they can be in a superposition of two states at the same time, as well, or also that they can be entangled. There can be two particles that are doing exactly the same thing. When you measure them, they do exactly the same thing. So this is what you can do in such case. So for example, if you have two coins, right? Assume a simple case where your password is just heads or tails, right? And let's just break it down to that level, just for the sake of this illustration. So we want to make a password. We want to share a password. So I give you, you're on, you're somewhere on the other side of the earth, and I'm here in Glasgow, and I give you a coin, and I keep another coin, but these two coins have this weird sort of magic property of entanglement, right? So what it means is that if we flip our coins, if I get heads, you get heads as well. If I get tails, you get tails. Or better still, assuming we're using dice, right? I've got my die and you got yours, and I throw mine. If I get 1, you get 1. If I get 2, you get 2. If I get 3, you get 3. And our password is one of these numbers, right? So if we want to share a password, all we have to do is that I throw my die and I get a number 1 to 6, and I use that number as my password, right? I use that to encrypt the message, and when after encrypting the message, I send it to you. If someone gets the message, they don't know what number I used, so they can't crack the code. Of course, 1 to 6 is a very small sort of space, so if you try from 1 to 6, you'll find the answer. But in practice, you use a very large number. So I make this encryption, send it to you. When you get the message, to decrypt the message, you use the password. But you already have the password because your coin will do exactly what my coin did, or my die did. And you get the number, you decrypt the message, and all is well and good. Now oh yes, thank you very much. What's amazing about this whole process is that it's secure, right? When the information about what result I get when I throw the die is only known to me and only known to you. Nobody else in the universe knows this information. In the physical universe, of course, in the physical realm. You could say, oh, God knows. Yes, okay. But we're talking about, in the physical realm. And basically what it does is that it gives you a way to share passwords securely. It's completely robust. It's, tamper-proof. If anybody tries to listen, it kind of self-destructs, it kind of collapses and it doesn't work anymore. It's really, really easy to detect that someone has listened. And then when you detect someone's listened, you don't use that password and you're safe. Your information is safe. So that's a basic idea of how it works, okay? It's, of course, a lot more detailed than that, a lot more precise than that. But that's the basic idea. There are other protocols that you use in quantum key distribution, but the entanglement-based one is a nice one to use to describe what happens. But at this point, we're going to listen to a song that's very coded. It's entitled Lagos Anthem by Zlatan. And we'll be right back and talk about quantum sensors. Abracadumba. Yes, that was Zlatan with Lagos Anthem. And it's a really nice song to use in this part of the show because we're talking about quantum magic and we're talking about some of the terminology, some of the jargons that we come across in quantum science and technology. We've talked about qubits, we've talked about quantum entanglement, we've talked about superpositions, we've talked about quantum key distribution. Now we're going to talk about quantum sensors. Of course, this is what we do on the Science Show with Dr. Dada, and we're broadcasting live from the city of Glasgow. And of course, because it's the International Year of Quantum Science and Technology, we'll be focusing a lot on quantum science and technology this year. So stay tuned, stay locked onto this show in the weeks and months to come. So quantum sensors. What are we talking about when we talk about quantum sensing? Well, it turns out that, the properties of quantum systems, so these qubits, these entangled particles, they allow us to do, very, very interesting things. Like, we mentioned quantum cryptography already. It turns out that when you want to sense things, for example, when you want to image things, there are things you can do that otherwise are impossible without quantum properties. For example, quantum entanglement. So, for example, if you want to sense how thick a piece of glass is, just as an example, or how thick a medium something is, maybe the constituents of a fluid or the composition of a fluid. One way you can do that is by passing light through it. And when you pass the light through it, you can measure the distance that the light passes through, and that distance, the optical path length, as we call it, it depends on what we call the refractive index of the material. So for example, if the fluid or the material has a high or large refractive index or small refractive index, that determines whether the light comes out a little bit later or a little bit sooner. And this sort of path length or phase that this material imprints on the light is a very powerful tool for measuring properties of materials. And we use that in so many different fields, in biomedical imaging, in sensing. A lot of it is to do with interaction of light with matter, interaction of light with materials that light passes through it, and based on its composition you see that the light acquires a phase. A very good example is, for example, if you're measuring in a liquid the concentration of some solvent, maybe sugar or salt or whatever. So these solvents, salt or sugar dissolved in the water, which is the solvent, gives you a solution that has a different refractive index to ordinary water, and the amount of salt or the amount of sugar you have in it might change the refractive index. And so by passing the light through it, and in a clever way, you can find out the refractive index from doing that, and from that you can infer how much salt or how much water is in that solution. And so this kind of sensing is very useful for things like medical diagnostics. So if you have a urine sample, there are things you can do, different other tests you can do, or even you're measuring a film where you've got cells and you've got other structures, and you can image these things using properties of light and how these things interact with the light. Now, the interesting thing is this: if you have a situation where the light that you're using is not ordinary light, it's not just a light from a lamp like we have here, or it's not even a laser, it's not just a laser, but it's potentially entangled photons. So photons are the small grains or particles that light is made up of. If you have a situation where the photons are entangled, what happens is when the photons interact with the medium, they interact as one object. They don't interact one by one. So what that means is when the photon picks up a delay or a phase because of interacting with some solution or a material with a different refractive index, then what happens is that the effect of that change or effect of that solution is doubled. If you have photons that are two photons entangled, the effect it has is doubled. If it's 3, it's tripled. If you have n photons entangled, then the effect, the sensitivity is n-fold. And this is super powerful. This is really, really useful. It means with very little light, you can increase the sensitivity of your measurement. And you can easily see how that's useful. For example, in biomedical imaging, where you want to image live cells and you don't want to shine too much light on them because you don't want to kill them. Normally, the more light you shine, the better you're able to see. But if you have a limit on the amount of light you can shine on these samples, then you want to use entangled photons, because then that means you get more bang for your buck. You've got n photons, and because of the enhanced sort of sensitivity, n-fold enhancement in sensitivity, it means you can do things that are impossible to do classically. So you can image these things, you can image brain cells, you can image deep inside the brain, you can do a lot of really cool things. So this is just a hand-wavy explanation of what quantum sensing does and how it works. There are many other aspects to it. You've got remote sensing, where you can send single photons and detect photons one at a time. You've got entanglement-based sensing, whereby you use the fact that you have entanglement between one point and the other to, detect to detect things remotely. There's so many things, so many applications. Imagine, for example, driverless cars that can see road changes or obstacles far better than a human, based on quantum technologies, maybe using quantum light, using entangled photons. So it's so amazing. The prospects are so massive. The potential applications are so many. Of course, we're still perfecting how to make use of these sensors, how to make them stable, how to make them affordable. So you can't just grab a touchlight, a quantum, touchlight or anything like that yet. But the race is on. Researchers are working worldwide, and they're trying to shrink and toughen and fine-tune these quantum sensors so that they can help us more and more in our everyday lives. So we'll leave it at that on quantum sensing, and we're going to take another music break. And this time we're going to be listening to another song that's been quite popular in recent days, recent weeks, and it's entitled Venus by Faceless and Serotonin. And we'll be right back. Yes, that was Venus. I wanted to say that was Shenanodinayamo. But the title of the song is Venus. It's really, really relaxing, very soothing song. I love the voices, love the arrangement. It's just really nice. So, yeah, I think these guys are going to do really well in the coming months and years. It's nice to look forward to what they're going to come out with. So that was Faceless and Serotonin with Venus. And this is the Science Show with Dr. Dada here on Jambo Radio Scotland, broadcasting live from the city of Glasgow. We'd like to take this opportunity to thank you, our listeners, for tuning in. And if you've been with us from the beginning, thank you so much. It's really nice to kind of engage together, talk about quantum things, quantum science and technology, and other aspects of STEM. As you know, we do that on the show, from biology to, mathematics to chemistry to, engineering that's based on, these sciences. And it's a really nice forum to discuss developments in these areas. And you're always welcome to join the conversation, of course, as you can see on the screen. For those watching, you can call us. For those listening, there's time to call us in this final section of our show tonight. You can call us. The number is 0141 530 2787, and that is 0141 530 2787. You can call and chip in, tell us how you're feeling, tell us what you find fascinating about quantum technology, what you think. Do you think it's a hype? Do you think the bubble is going to bust soon? Do you think it's the future? I would like to hear your views and your thoughts as well. So we've talked about a few things. We've talked about, qubits, entanglement, superposition. We've talked about quantum cryptography, and we've talked about quantum sensing a little bit. So we could talk about quantum computing. Finally, we can sort of say one or two words about quantum computing. And I think what I'm going to say about it very briefly is, you see, quantum computing is basically like a computer. It uses the superposition principle to build a computer that is able to solve multiple problems at once. Now, I say that with a little bit of, you have to be careful what you say, because that is in principle true. But at the end of the computation, you can only get one result. So, it's not immediately obvious how to take advantage of this effect. So as we said before, quantum systems can be in multiple states at the same time. I'm using air quotation, because it's not really at the same time as such. It's like it's not decided which one it is yet. So it's a similar effect in quantum computing. So the speed, so a quantum computer can be so much faster in solving certain problems than the normal or ordinary or classical computers that we have, because you can have this situation where your problem or your computer can do multiple things at the same time, or maybe more accurately, it doesn't decide which one it did until the end of the computation, until you do the measurement, right? So it's like it's kind of said, okay, I'll decide which one I did later. I'll just be in a superposition of all of them, and then at the end you can do a measurement that checks the answer, and then it decides, okay, I did, or you can sort of tease out the answer in some clever way if you do a clever measurement. So that's pretty much how it works. And of course, quantum computers are not better than classical computers in every way, in every problem. There are very specific niche problems that you can solve with quantum computers, and that includes things like search problems. It includes things like factoring large numbers. So problems like that, problems that can be broken down into these forms, benefit from the power of quantum computers. So again, it's about performing the computation, performing an operation on a state that's in a superposition of different forms, different states. And you can easily kind of envisage how that helps with searches. So if you want to search a maze, instead of going through one path at a time, that takes a long time. If you go through all the paths, you can find the solution. You can find what you're looking for much faster. So that's kind of the idea behind quantum parallelism or quantum computing and how it works. And in future shows, we're going to talk more and more about this, the cutting edge development, the involvement of various, research organizations in the UK in, quantum science and technology. That's all coming this year, as it's the International Year of Quantum Science and Technology. And before we go, we're going to crack a couple of jokes, as we usually do on this show. And let's just see whether you can get any of them right. So they're in form of questions. The first one, are you ready for this? Yes, I'm ready. Well, the first one says, why did the quantum computer break up with its classical girlfriend? Why did the quantum computer break up with its classical girlfriend? Yes, I'll give you a moment to figure out the answer to that one. Well, the answer is because every time she looked at him, he collapsed into just one state. Yes, thank you very much. That's the answer. So it's an interesting one because, as we said, quantum systems can be in a superposition of two states at the same time. And when you measure them, they have to give you one of the answers. They can't say, oh, I'm not sure. When you ask the question, are you in 0 or in 1? Then it gives you an answer. So that's called the collapse of the wave function. And so perhaps you've heard that before. So when she looked at him, he always collapsed into one state. So that's the pun there. Good. So the second one, right? Why don't quantum computers ever get lost? Let's see if you can figure out the answer to that one. We kind of touched on it a little bit with the previous part, the part we just mentioned about quantum computing. Well, the answer is because they're always exploring all possible paths at once. Yes, thank you very much. And it's so true. And in fact, this joke is really not a joke. It's pretty much what it is. It's pretty much accurate, this joke, which I like very much. Anyway, that's all the quantum comedy that we can take for today. And it's all about superpositioning the punchlines, isn't it? So quantum jokes that are funny and not funny at the same time, as we've said in the previous episode of this show. So, of course, our show is all about STEM. If you're enthusiastic about STEM, if you want to know what's the cutting edge science and technology, what's going on in that sphere of life, this is the place to be, the Science Show with Dr. Dada. And we'd love to hear from you. So you can share your questions with us through our various channels. And to conclude this show, we're going to play out a song. And the title of the song, are you ready? Is by Tana Musica. It's called Kutu Wenje. And with that, we'll say good night. And we'll see you next time.
Yeah. Tana Musica lo de yo, yeah. Arrest Jabata, yeah. Because of you, my darling. All the while I be your Charlie. All the crazy things I've seen, my darling. To be with you, my daddy. I no go figure cool it. Hey, baby, you the one for me. You the only parcel of me. And what you they do to me, you they driving me crazy. Baby, there's no fighting this. You're the only parcel of me. And until eternity, now you go there for me. Abakorimaka, I grow goatee like that, I go to Timbuktu, only because of you, I go to NJ, only to stay. I just have to see your face, and any other day I